Hey guys, so last week's video didn't work out very well, so I figured I would try to make you a quick video that would cover both Graham's law and the ideal gas law. So Graham's law we did on Friday, ideal gas law we will do today, but this quick video is just going to cover both of those laws and try to help you out a little bit with how the math works. So Graham's law is pretty straightforward. It's all about how fast gases go. The little numbers have to do with the two different gases. Rate means the speed, which is measured in meters per second, or anything else, doesn't matter as long as you keep it the same. And M stands for grams, mass, however much you have. So the smaller a gas is, the faster it goes, and it goes with this. So how you use Graham's law is you need to have a race between a couple different elements. So let's say we have a race between oxygen and fluorine. If oxygen and fluorine have a race, we want to know who's gonna get to the finish line first. We need to know who's the fastest, and so we compare these two rates. So we don't have the distance here. So let's say that it took oxygen 10 seconds to travel 1 meter. So that would be, or excuse me, let's say 1 second to travel 10 meters. So that would be 10 meters per second for the rate of oxygen. So for oxygen, my rate 1 would be 10 meters per second. I want to know how fast fluorine is. So that's what I'm going to look for. That's my unknown. And then you just put your masses off the periodic table in the rest of your formula. So 1 is oxygen, so oxygen is going to be on the bottom of your fraction here. Mass 1, rate 1. Oxygen is 16. There's 2 of them. 16 times 2 is 32. Fluorine is 19. There's 2 of them. 19 times 2 is 38. Okay? So I'm going to do some quick math in my calculator here. And I'm going to say 38 divided by 32. Take the square root of that. And I get 1.089. So 10 over my rate that I want is 1.09 if I round. Multiply rate by both sides, and get this rate. Get that rate. Oh man, it didn't let me take it. Okay, multiply rate by both sides, get the rate on the other side, which is going to get it. And you say 10 divided by 1.09 to get your rate. 10 divided by 1.09 is going to equal 9.17 meters per second. So fluorine is just a little bit bigger than oxygen and just a little bit slower than oxygen. So all you have to do is just plug things into this formula. For Graham's law, you can find how an unknown by finding its mass. You can find how fast something is compared to something else with your rate fraction. Just make sure that you keep whatever this is with this mass and whatever this is with that mass. Okay? Next thing we're going to do is ideal gas law. To me, ideal gas law is pretty straightforward because it gives you everything. The ideal gas law is PV equals nRT. And ideal gas law just tells you about a gas. And this is everything you need to know about a gas. P is your pressure. It's going to be measured in kilopascals. Volume, V is your volume, measured in liters. N, let's put everything in red over here so you have a little bit different. N is moles, measured in moles. Pretty straightforward, how much you have. R is one of the easiest ones because it's your constant. It's always going to be the same, 8.314. It is the ideal gas constant. It's no matter what you're doing, as long as you're using kilopascals, R is 8.314, and T is temperature, but this is huge. Temperature measured in kelvins. Temperature in kelvins. Okay, now that's a real quick little formula for kelvins. Kelvin is just your degrees Celsius. Degrees Celsius plus 273 equals Kelvin. And you do that because technically temperature can't be negative. Particles are always moving. So 0 is as low as you can go. 0 K is the lowest temperature possible, and that is negative 273 degrees Celsius. So once you have all this, it's just a matter of plugging in what you don't know and mathing it up to get what you want. So let's say you have let's say, what we're going to say, let's say 20, say they have 32 grams of oxygen. 32 grams of oxygen at 207, or let's say 0 degrees Celsius. At 0 degrees Celsius. 32 grams of oxygen at 0 degrees Celsius and 101.3 kilopascals. Okay, 32 grams of oxygen at 0 degrees Celsius and 101.3 kilopascals. What is your volume? So it's just a matter of plugging everything into this nice, pretty formula right here. P, V equals nRT. All right, P is pressure, 101.3. V is volume. That's what I'm looking for. So I'm just going to put V. N is number of moles. Now, it doesn't tell me number of moles, but it tells me something I can get moles from, which is grams. Real quick, 32 grams of oxygen. I don't want grams. I want moles. How many grams in a mole of O2? 16 times 2 is 32. Easy math. 32 divided by 32 is 1. So I got 1 mole in. R is 8.314. When we do math and chemistry, I really like parentheses better than dots or X's for multiplying. Just keeps things nice and pretty. And then we go to T, 0 degrees Celsius. I don't want Celsius, I want Kelvin. So I add 273, 273 K. So it's just a matter of mathing this up. 101.3 V equals 273 times 8.14. Is 2269.7. Okay, math this up. That number divided by 101.3 is 22.4 liters. And if that sounds familiar, it's because it's the number we used all the time when we talked about having 1 mole of any gas, 22.4 liters. PV equals nRT, all about plugging and playing numbers. That's all it is. If you want to see more of these problems, join us in the Zoom and we'll do a lot more examples. But that's a real quick little video to kind of help you with those two things. Have a great day, guys. Like I said, join us on the Zoom each day, right around 12:30 each day. Have a great day.